This lecture is on atomic weight. What is atomic weight and why should I bother learning it? It's useful for figuring out how many grams of sodium I need to react with chlorine without a lot of waste. It also tells me what is really going on in nature. Are isotopes unusual or are isotopes the norm? And given a pound of uranium, knowing its atomic weight, I can use it to calculate the number of atoms. It all goes back to conservation of mass. In a closed system, the mass of the products must equal the mass of the reactants. It starts with the chemical formula. Some of you may know what that is. That is caffeine. You first write the chemical formula. This tells you how many atoms are needed for each substance. In other words, it gives you the ratio. Like if it was water, you need 2 hydrogen atoms for each oxygen atom. Then next, you write the reactants and you write the formula for them. Sometimes reactants only come pre-packaged. If you're not clear on what I mean by pre-packaged, please review the Balancing Chemical Reactions video. Then you balance the equation so that the same number of atoms are on either side of the yield sign. I want to create substances. I'm an artist after all. This is Durham School of the Arts. Artist creates. Well, then you can use the atomic weight to figure out how many grams of gravy you need to create your buffet dinner for 12. Oh, you're not talking about culinary artists? Well, yes, there are other artists. Well, they also need to know the formulas and atomic weights to figure out paint. See the beautiful colors in that? They were all hand ground. Well, how much of this do you use? How much of that do you use? Knowing chemical weight helps you create an accurate reaction. When most people think atomic weight, they hear the word weight. Weight does not mean weight as in gravity. Many people object to the term atomic weight, and they'll use other terms, and I agree with them. I don't like the use of the term either. Atomic weight, because weight is the pull of gravity, and atomic weight has nothing to do with gravity. The IUPAC definition is the atomic weight of an element from a specified source is the ratio. Ratio meaning how many proportions they are, the ratio of the average mass per atom of the element to 1/12 the mass of an atom of carbon. So you take a normal carbon atom, and how does this compare to that? There's a lot of problems with this definition. For one thing, specified source. What? You're worried about the specified source? Isotopes are considered in the atomic weight calculation. So the atomic weight is not per atom. It's based on isotopes found in nature. It uses the average mass from a specified source, which means boron from Turkey has a lower atomic weight than boron from California due to the different amounts of isotopes. So atomic weight is useful for doing chemical reactions. And again, this is all because we can't determine a specific atom. We don't have that kind of accuracy. So we use the best we can, and atomic weight is a nice way to use the best we can. So let's look up a close-up of hydrogen here. Since the mass of an atom comes from the protons and the neutrons, so there's the protons and the neutrons, that makes the mass. What does this tell you about hydrogen found in nature? The mass of hydrogen and a neutral hydrogen atom would be one proton plus 1 neutron. So its atomic weight should be the atomic mass, which would be 2. But atomic weight isn't just atomic mass. Atomic weight is the masses found in nature. So if the atomic weight is 1, what's that tell you about how it's found in nature? Well, it's missing neutrons. It's got to have the proton or it wouldn't be hydrogen. Most common hydrogen found in nature does not have a neutron. Why do we need to know this? Because if we wanted to make something, everybody uses the atomic weight to guess at what the ingredients are going to look like. If you make a cake, you got to have so much flour or so much sugar. That's going to be different than if you're going to make a scone or a muffin, but they all use flour and sugar. We want to make something, and so we need to know what the ingredients are. You don't want to guess trial and error with some of these things. It can be quite dangerous, especially when you can use math and figure it out. We use the formula to determine how many atoms are needed of each element, so that's why it's important to balance. And then atomic weight doesn't actually have a unit. It's not in grams, meters, any of that stuff. We can pretend the atomic weight is in grams or pounds, and we can use that for our calculations. So we have the same number of atoms on both sides of the yield sign. You can't pull oxygen out of thin air. You can pull oxygen out of thin air because air has oxygen in it, but it doesn't have mercury, it doesn't have gold, it doesn't have any of the other elements that may wish to use. And Lavoisier was the first one who realized that, yes, gas is an element and you need to include it and when you balance equations. So in a closed system, you can't pull oxygen out of nothing. So here's our example. What if we needed salt for our mashed potatoes, but we didn't have salt, couldn't get to the store, but we just happened to have hanging around a canister of sodium and a canister of chlorine. Now, both are poisonous, so you really don't want these hanging around. But what if we did? The formula is Na plus Cl equals NaCl. And is that balanced? What's the charge for sodium? What's the oxidation number for sodium? It's 1. And how about for chlorine? -1. We should write plus there. This is a metal, so you have to do a crisscross to figure it out. So 1 goes to there, 1 goes to there, and you're left with Na1, Cl1. You get rid of the 1s, and so it's NaCl. So this is a completely balanced equation. So now that we have a balanced equation, we look at the atomic weight. So you go to the periodic table, and you look at the atomic weight for sodium, and it's 23. 23 is unitless. It's not in grams, it's not in pounds, it's not in meters, not in anything. What is it for chlorine? Go ahead and take a minute, look at the periodic table and find it. Chlorine's atomic weight is 35. Again, this is not a measure, it's unitless. Pretend these units are grams, and we have 23 grams of sodium, and if we had 23 grams of chlorine, if we put them together, we would get 58 grams of sodium chloride. Let's try another one. Let's say we were stranded out in space. Oh no! In space we have no water, but in space we probably do have hydrogen gas and oxygen gas because you combine those to make fuels. What to do? What to do? Well, let's look at the formula for hydrogen and the formula for oxygen and the formula for water. Is this balanced? No. If you remember, a way to do this, there's lots of ways to do it. I'm going to put oxygen, and I have 2 on this side, because that 2 means it comes in sets of 2s. But I only have 1 on this side. Oh, not good, not good. That's not going to work out. It's not equals. So I've got to do something, so let's make this a 2. So I make that a 2, and now this is 2 over here. Okay, those balance. Now let's try our hydrogens. Over here I have hydrogen, and I have 2 of them. So I have 2 hydrogens. There's 2. But I have 2 of those. So I actually have 4. Is that balanced? Oh, no. What can I do? That 2 does not equal 4. But if I change this to 2, now I have 2 times 2, so I have 4 on this side and 4 on that side, so now it's balanced. So this is the balanced equation. Now that I have it balanced, now let's look at the atomic weight. So the atomic weight of hydrogen is 1. That's a really easy one. Atomic weight of oxygen, make sure you need to check that out, it's 16. So pretend the units are grams. Again, they don't mean anything, they're ratios, so we can use them for a lot of things that we want to. So pretend they're grams, and we have, okay, just to show you where everything's coming from, we have, here's the atomic weight of hydrogen, came packaged as 2. That's what, and then oxygen, and it came packaged as 2 also. Okay. Here's the hydrogen, there's 2 of them. Here's the oxygen, there's only 1 on this side. And remember the order parentheses. This is now prepackaged, and we have 2 of them. So we do the calculations. We have 4 grams. Here's 2 times 1 is 2 times 2 is 4. Then over here, 16 times 2 is 32. So 16 plus 2 is 18. 18 times 2 is 36. So if we had 4 grams of hydrogen and we combined it with 32 grams of oxygen, we would now have water to drink. We would be very happy with 36 grams of water. In summary, chemical behavior, you know, is determined by atomic number. That's the number of protons that's in an element. To create a reaction, we would like to use atomic number directly, but we can't. We cannot measure atoms directly one for one, so we have to use approximations. Since we can't measure atoms directly, we use the atomic weight, the approximation of atomic mass as it is found in nature. Given that and the formula, we can estimate how much reactant we need and how much product we will get out of a reaction. For further information, I like this site. Enjoy.